All right, so this part of solving equations, we're going to do general solutions, which means we're not going to restrict our domain to a lap around the unit circle or something like that. So we'll start with something basic so that we can figure out what's going on. So I have the sine of theta is going to equal -1/2. Okay, but I am not restricted on my domain, which means there's an infinite number of places that this can happen. So first thing we want to do is recognize what the period of the sine function is. The period of sine is 2 pi. This is going to occur twice within one lap of the unit circle. Okay, so I need to find those two places, and then we'll generalize. So the first place that sine is equal to a -1/2 is going to be at 7 pi over 6. And the second place it's equal to -1/2 is going to be 11 pi's over 6. So I can add a lap to this, and it's going to be coterminal with 7 pi over 6. I can add a lap to this, and it will be coterminal to 11 pi over 6. I can also go backwards a lap, and it will be coterminal with 7 pi's over 6. So we identify the places within one lap of the unit circle, and then we generalize. So I need to add integer multiples of a lap. I need to add integer multiples of 2 pi. So I am supposed to add 2k pi to that. So in other words, if k is 0, then I'll have 7 pi's over 6 plus 0, which is 7 pi over 6. If k is -1, then I'll subtract this and I'll get -5 pi over 6. Okay? So if I have 2, then I'll do 7 pi over 6 plus 4 pi's, which is 2 laps. Okay? So then I'm going to say the same thing for this one, plus integer multiples of 2 pi. So because in one lap of the unit circle, which is the period of sine, this occurs twice. I represent the two places that it occurs, and then I say plus integer multiples. From there, it wants to find, or we're supposed to find the first 6 solutions. Okay, so I'm going to put a 0 in here, a 1, a 2, a 3. A 0 in here, a 1, a 2, a 3, and then I'm going to find out which ones are the first 6 smallest. Okay, so I've got 7 pi over 6 plus 0 is 7 pi over 6. 7 pi over 6 plus a 2 pi, 2 times 1 is 2 pi, which means 12 pi over 6. So a lap is going to be 12 pi's over 6. So 7 pi over 6 plus another lap is going to give me 19 pi's over 6. Okay, and let's do another lap just for fun. So 19 pi's over 6 plus another lap is going to be, what is that going to be? It's going to be 31 pi's over 6. Okay, and then let's just do one more just for kicks. So we've got 12 pi's over 6 plus 31 pi's over 6 is going to be 43 pi's over 6. Okay, now we're going to do these ones. So I'm going to add the first, I want the first 6 smallest representations. So I did 4 of these, and I'm going to do 4 of these. So 11 pi's over 6 plus 2 times 0, then 11 pi over 6 plus 2 times 1 pi, 11 pi over 6 plus 2 times 2 pi's. Okay, so for the first one, I'm going to get 11 pi over 6 plus 0 pi's. The second one, I'm going to get 11 pi over 6 plus 2 times 1 is a lap. So 11 pi's over 6 plus 12 pi's over 6 is going to be 23 pi's over 6. And then add another lap to that. So add another 12, I get 35 pi's over 6. And then just for kicks, we can do it one more time. So 35 pi's plus 12 pi's is going to be 47 pi's over 6. Well, now here's the easy part. I just need to look and get them in order. I need the first 6. So here's, since they're all pi's over 6, they are multiples of pi over 6. I've got, this is the smallest one at 7. Then I've got 11 And then I've got 19, so there's my first 3. Okay, and then I'm going to go to 23. So there's my first 4, and then I'm going to go 5 and 6. So those 2 were extra. So those are my first 6 answers to where does the sine of theta equal -1/2. There's an infinite number of answers, which is how we represented this. And then here are my first 6. Those are the first 6 smallest answers. Okay, so let's try it again. We have that, wrong way. We have the tangent of theta is -√3. So first of all, I want all the general solutions, and then I'm going to write the first 6. Okay, so first of all, what's the period? The period of tangent is 1 pi, and -√3 occurs once. Okay, -√3 occurs once in that interval. So looking at tangent theta of -√3, where's the first time in a lap of the unit circle that my tangent is negative? It's going to be in quadrant 2, and it's going to be at 2 pi over 3. So theta is 2 pi over 3. So because your period is 1 pi, I'm only interested in the first top half of the unit circle. I'm not talking about inverse trig functions. So don't sweep down to -pi over 2 and go up to +pi over 2. I'm looking at, if I look at one lap of the unit, that was lovely, one lap of the unit circle starting in standard position, where's the first time that tangent has a ratio of -√3, and that's going to be at 2 pi over 3. All right, now because it repeats every pi, this only occurs once in the period of pi. Okay, so backtrack for a second. This occurred twice in the period, so I had to represent it twice. Okay, this occurs once in the period, so I only need to state the first thing, because now I'm going to do integer multiples of pi. So how do I represent integer multiples of pi? I'm going to say pi k. So again, the period of tangent is 1 pi, so I'm going to do integer multiples of pi. In other words, if I add 0 to here, 2 pi over 3 plus 0 is 2 pi over 3. Okay, but add a unit of pi. Okay, so a single unit of pi is going to be 3 pi's over 3. A single unit of pi based on a denominator of 3 will be 3 pi's over 3, because that reduces to a pi. So if I do 2 pi over 3 plus 3 pi over 3, I get 5 pi over 3. I'm still in one lap of the unit circle. Okay, but because the period's pi, I just need to represent it once. So now we want to know the first 6 representations, with k being my integer multiples starting at 0. So I'm just going to add multiples of 3 pi over 3. So I've got 2 pi over 3, which is where k is 0. Okay, so now make k 1. So 2 pi's over 3 plus 1 pi is going to be 5 pi's over 3. Okay, plus another 3 is going to be 8 pi's over 3. Plus another 3 is going to be 11 pi's over 3. 14 pi's over 3. And then we need one more, which is going to be 17 pi's over 3. So this is your general solution. That represents the infinite number of places where tangent theta will give you at a ratio of -√3. And starting at k equals 0, these are the first 6 places. So the next problem that we're going to work through is going to be the sine of 2 theta equals 1/2. Okay, so first of all, what is the period of my trig function? The period of my trig function is 2 pi. Okay, I need to find all the places where sine will give me a ratio of 1/2, positive 1/2. So I'm in quadrants 1 and 2. And then I'm just going to do a few more because I know that I'm going to have to divide this 2 out. Okay, so where does sine equal 1/2? Sine equals 1/2 at pi over 6, and again at 5 pi over 6. Okay, and now I need to do integer multiples of those. So I need to add a lap, okay, because I may need to have additional representations within one lap. Okay, so pi over 6 plus 12 pi's over 6 gives me 13 pi's over 6. Okay, so what I'm doing is I'm watching to see what happens with my denominator, because I'm fixing to divide by 2. So this is going to become a pi over 12, 5 pi over 12, 13 pi over 12. So let's do this one. Add a lap, that gives me 17 pi's over 12. Okay, which I haven't done the over 12 yet because I'm just telling you where we're headed so I know where to stop. And then I'm going to do, so I added a lap here, I added a lap here, let's add another lap here. So I've got 13 pi's over 6 plus a lap is going to be 25 pi's over 6. That means I'm out of one lap, okay? Because that'll give me 25 pi's over 12 when I actually do the division, which is more than one lap of 24 pi's over 12. So what I have here is what I actually have is a 2. So I'm going to divide by 2 all the way across. So now I have theta equals pi over 12, so that's what I was screaming about, 5 pi over 12. And then I've got 13 pi over 12. And then I got 17 pi over 12. Okay, so I want to look for a pattern, because if I go any further, I'm going to be outside the unit circle. In other words, if I add another lap here of 24, I'll be way outside the unit circle. I don't want to be outside one lap of the unit circle. So I need to see if there's a pattern here. Well, to get from here to here, I added 12 pi's over 12. Okay, I added a pi. So from here, I can take my first one plus pi k. Okay, so I'm going to represent how to do this, and then I'm going to look at the next one. How did I get from here to here? You're looking for a pattern. Well, I added 12 pi's over 12, which is 1 pi to this one. What did I add to this one? I added 12 pi's over 12. So from 5 pi over 12, I added integer multiples again. So these are your general representations. And now what I need to do is give the first 6 solutions where k is 0, 1, 2, 3, 4, 5. Okay, so I'm going to go ahead and just fill these out, and then we're just going to take the first 6. So I'm going to do 4 of these, and I'm going to do 4 of these, and then the first 6 smallest ones. Okay, so I've got pi over 12 plus a pi is going to be pi over 12, plus 12 pi's over 12 is 13 pi's over 12, plus pi over 12 is 25 pi's over 12, plus pi over 12 is 37 pi's over 12. So I've got the first 4 iterations of this one. Now I'm going to do the first 4 iterations of this one. I'm going to pull the 6 smallest. Okay, so 5 pi's over 12. So 5 pi's over 12 plus a pi over 12 is 17 pi's over 12, plus 12 is going to be 29 pi's over 12, plus 12 is going to be 41 pi's over 12. So I want the first 6. So I've got a 1, a 5, I got a 13, 17, and I got a 25, 29. So those are the first 6 iterations. So remember, they're multiples of pi over 12. So I've got 1 pi over 12, 5 pi's over 12, 13 pi's over 12, 17 pi's over 12. And then I got so on and so on. So this was extraneous. I didn't need to do that. But these are your general solutions. So theta equals that mess. And then these are the first 6 solutions that are going to work with your with your k values, with your repetitions. Sorry, that was a jumbled mess. All right, so we're going to do a third video.